Well then, I just recorded like 11 minutes of video and my camera stopped working and we had so anyways, I'm back and most of the worksheet's done, but not from your perspective. So let's jump into this and I'll kind of talk through the thought process. I'll just talk through what I did here. So look, all of these ask for the pH of the solution, which is a very common thing to report. Like pH is just kind of a commonly used for comparison of acidic and basic solutions. Like that makes sense. Now, the way you calculate pH is you take the negative log of the hydrogen ion concentration. So if they give you the hydrogen ion concentration like they did up here, finding the pH is like super duper easy. But the way that they give you this, you have to think about the solution that forms just a little bit. So what I did is I went through and I drew or wrote an equation for the formation of the solution. So this one told me I was doing a hydrochloric acid solution. And hydrochloric acid, when it forms ions, it forms hydrogen ions, which is what makes the solution acidic, and chloride ions. And I know hydrochloric acid is a strong acid, so for every mole of hydrochloric acid that I put in, I'm going to get a mole of hydrogen ions. So I did, just wrote out this little chart to kind of show that. And, if I put in 0.01 molar hydrochloric acid, then I will form 0.01 molar hydrogen ions, because for every one hydrochloric acid molecule that goes in, I get one hydrogen ion. And then, okay, now I have... All right, so now I have the hydrogen ion concentration, so I can plug into the negative log of H plus to get the pH, and I do that, and I get 2 for the pH. And sorry for the interruption there. I had to go save a lizard in the hallway. Blue-tailed skink, if you want to look up a picture of one. Oh, it's fun. All right, so now number 2 is a little more complicated just because they gave me a base that I'm adding. And so when I add the base, it forms sodium. This sodium hydroxide is going to separate into sodium ions and hydroxide ions. The hydroxide ions are what contribute to this being a basic solution. You might note I've been doing the 0 with the star there. That just means that to start with, there are a few hydroxide ions in solution just because of the autoionization of water. We talked about that in class. The concentration is 10 to the -7th, which is a lot less than, that's like still a factor of like 10,000 less than the amount of hydroxide that I'm adding to it. But the same kind of concept here. If I start with so what I'm getting at here, I can ignore the hydroxide that's in the water to start with just because of the autoionization of water. So if I put 0.001 sodium hydroxide in, for every one I put in, I get 1 hydroxide. So the amount of hydroxide is the same as that number. And then this time, though, I've got hydroxide. So when I take the negative log of hydroxide, it gives me pOH. So once I get the pOH, then I have to do this equation. I have to do the pH plus pOH equals 14 and subtract the 2. And, I'm doing 14 minus the pOH to get the pH. Now, let me make a note about significant figures for these. So if you have 2 significant figures in your concentration that you use, you should have 2 digits reported after the decimal place. I messed that one up, so it should be 11.00 to report it to the correct number of significant figures. I know that's a little bit weird, but that's how significant figures work when you take a log of a number that has significant figures. By the way, this 14 is exact, so it doesn't contribute to significant figures, so I don't have to round to, no significant figure, or no points after the decimal place because of the 14. So Basically, just however many significant figures the concentration has is the number of decimal places you should report after the decimal point in the pH. So, now getting more interesting, I guess, the strontium hydroxide, it's also a strong base. Strong base, strong acid. This is also a strong acid. That's why I didn't tell you anything about ionization. We'll finally get around to that over here. So that one, for every one strontium hydroxide you put in, no, there's 2 hydroxides there will be 2 hydroxide ions that are produced. So if I put in 0.05 molar strontium hydroxide, the actual hydroxide concentration will be twice as much as that. So this number times 2 gets you 0.10. And then you got the hydroxide, you can take the negative log of it to get the pOH. Once you have the pOH, subtract it from 14 to get the pH, and reported 2 digits after the decimal point there because the concentration had 2 significant figures. So that's how you report the correct number, significant figures for that. Another strong acid down here, similar process. I just kind of gave up on writing the zeros because it's like, okay, I know I'm starting with 0. This was a 1-to-1. That was a strong base, also a 1-to-1. So I went through and did the process on those. And I did that acid too. That strong acid is the same as the other acids here, the nitric acid separating. Now, once we got to the ones that were not strong acids, so acetic acid is a weak acid, hydrofluoric is a weak acid, nitrous acid is a weak acid. They had to tell us something about how much of the acid ionized. So if you assume 5% ionization, what that means is if you put in 2 molar acetic acid, only 5% of it is going to form ions. How did I get that number? Changed 5% to a decimal, which is 0.05. I did 2.0 times 0.05. That gives me 0.1. And like, where did I get 1.9 from? Well, that's the 95% that's remaining. So, you can look at that and see it's a 1-to-1 and just like, okay, I'll subtract that from 2. Or you could go 0.95 times 2 and it'll give you 1.9. Do you even really need that number? No, you don't really need the amount of acetate ion either. You really just need the hydrogen ion. So that's really all I needed there. Take the negative log of the hydrogen ion. That gives me the pH is 1.00. Reported to 2 places after the decimal because the concentration had 2 significant figures. Did something similar for the HF and the HNO2. None of those were particularly interesting. And finally, I've got this ammonium hydroxide, which is a weak base. So I'll go through and take care of this, and then we'll call it good. The base, NH4OH, is going to form ammonium ions and hydroxide ions. So if we put in 2.50 molar, and we're just 0 and 0, and that's, there's a start there. There's a little bit of it, but the amount that we put in is going to be so much greater than 10 to the -7th that we don't really need to worry about that. So let's do that. 2.50 times 5%. And that's going to give us 0.125. And this is going to go down to 95% of its original value. So I'll show you that. All right, so 2.375. All right, and okay, so I have hydroxide concentration. So I just realized I forgot to draw that. Look at that. Okay, I have hydroxide concentration, so I can do pOH. 0.125. And that will give me that will give me 0.903. That's the pOH. Now, that's not the pH yet. I need to do 14 minus 0.903. And that will give me 13.097. And that is the correct number of significant figures because I had 3 in the concentration, and I'm going to go 3 places after the decimal place to report the mantissa of this number with the correct number of significant figures. All right, so hope that is helpful. And yeah, we had a base and it ended up having a pH of 13. That's reasonable.